All right, welcome back to AI for Cybersecurity. I hope you're having an awesome time so far. Next up, we have two speakers from TigerGraph. Please join me in welcoming them to the virtual stage.
Hi, thanks a lot, Patrika. This is Gaurav Deshpande. I'm the Vice President of Marketing. And with me is Abhishek Mehta. Abhishek Mehta leads our sales engineering. We are a advanced analytics and machine learning platform on connected data. The core technology of TigerGraph is the only scalable graph database for the enterprise. We are 40 to 300 times faster than the competition. We are foundational for AI and machine learning at over 60 Fortune 500 companies. We are designed for efficient concurrent OLTP, online transactional processing, and OLAP workloads, analytical workloads. We are available on-premise, and we are also available on Google Cloud Platform, on Microsoft Azure, as well as AWS. The companies that use us include some of the largest companies in Fortune 500 across all industries, and we have several cyber security resiliency leaders using us for guarding against cybersecurity threats. Let's go ahead, go to the next chart and look at three core elements that are made up of TigerGraph. So the first one is a distributed graph database. This is where we are connecting all data sets and pipelines. For the sake of cybersecurity, we will look at all of your machine log data, all of your server data, all of your network events, and connect those up to detect threats. I have a couple of other industry examples here. I'll just cover one. United Health Group, which is a healthcare customer. We have built a customer 360 for them across 200 different data sets and pipelines. So from small startups to largest companies, we connect across all data sets and pipelines and build you a 360-degree view of all of your information. The next component is the advanced analytics. I have an example there of Jaguar Land Rover, a luxury automobile manufacturer, where we've actually accelerated supply chain planning from 3 weeks down to 45 minutes. We provide advanced analytics when it comes to cybersecurity threat detection also. Abhi will cover that in just a moment. The third component, which is in fact one of the most important, because after you have connected the data sets and pipelines with distributed graph database, you have analyzed the connected data with advanced analytics. It's time to learn from the data. So this is where TigerGraph provides in-database machine learning, which is unique in the industry. None of the other graph databases provide that. A cyber resilience market leader is using us, multiple of them, to detect threats in real time, combining graph-based analytics and machine learning in the cloud. And of course, several large banks use us for cybersecurity also. With that, let me hand it off to man of the hour, Abhishek Mehta. Abhi, take it away.
Thank you, Gaurav. Hey, everybody. Abhi here, and thanks, Gaurav, for the introduction. Let me take you to the talk of the hour. Folks, if you haven't heard about Solargate, maybe it goes by various different names, you are definitely in a wrong conference. So this is the conversation of the hour. Lots of the companies around the world are suffering from this attack. Here are some slides, which are basically courtesy Microsoft. And what's happening, what we're going to do over here is I will walk you through a very basic overlay of what this attack is and how technologies like TigerGraph would have helped you a lot in detecting this way before time than it has been right now. So let's look at this right now. Very, very early stage. The very first thing is that the supply chain was compromised on the SolarWinds Orion platform. And what happened was one of the DLL, this attacker was able to put in some malicious software inside that DLL, and that gets downloaded on the devices where the command and control center was set up. The first command and control center was set up. And these devices were compromised, binaries were downloaded onto the system, your AVs were bypassed. And as the third step over here was that compromised devices were used to steal the credentials, escalate the privileges, and gain the ability to create new SAML tokens. And at last, the thing was, okay, they are gathering all the information, they are passing this data outside out of the command and control center, and they were, getting hold of your emails. They are actually exfiltrating the emails. So when you look at this whole attack in perspective in a very basic layman term, one thing which stands out, especially the last three part of this attack, setting up command and control center, fetching all the data from your internal network in a multi-domain attack, and passing off that information outside of your domain. Now, the challenge over here is that all of this was happening inside your network. The lay of the land, your infrastructure architecture, your overall application architecture were actually showing you the wolf, not crying wolf, that there is something wrong in your system, right? I understand multi-domain attack. It's very difficult to get hold of various different set of application logs and collate them together to drive some analytics on it. And then we went ahead and did some reactive approaches. You update your patches for your AVs, and they went ahead and mapped the pattern of this attack over onto your logs and came up with some suspicious activity reports. And these are all reactive approaches. This happened once the whole system the damage was actually done. Now, looking this into as a lay of the land inside your architecture perspective, inside your infrastructure architecture, this is what was going on, right? And this is more or less with everybody. You have in the gear, you have various different services which are running inside your company, right? And these services are hierarchical in nature, right? You got things like service called another service we call the third service, fourth service. So this is a hierarchy of services calling each other, which are running on some sort of server or some sort of database. Maybe the database queries are being fired. These services have their administrators, and administrators can be regular user or not who report to some other person. And all these people who report are part of your organizational architecture, right? I mean, there are email addresses associated to it. And again, back to the services, they're outputting some data, and this data is basically being stored in the URL format, being accessed by the third parties over the network. So this is an overall view of your infrastructure architecture. And what was happening inside is that the deep link analytic inside your data set were telling you that something is wrong. For example, a random user, a dormant user, a new user, whichever user it was, became active and was given administrative rights. And when they were given administrative rights, they were accessing some services which are either new or they haven't used it from a long time, or were using it in way better, way higher number than the standard deviation would allow. How many times a user accesses a service? Probably 20 times. Standard deviation is, let's say, between 15 and 25. And this guy is accessing the data set for more than 50 times a day. And then they're writing it to the output, which none of the services do. They're writing it to a file, and that file is generating some sort of minor alerts. So if you look at this system in perspective, which is coming out of which is a product of a human mind, which is very interlinked, interconnected, your application has no way of firing these kind of analytics, firing these kind of rules on top of your data set, and come up and say, okay, you know what, looks like here is a flag. This is not as per the normal pattern. This doesn't happen right now for any cybersecurity tool or any analytical tool built on top of your log file. And the simple reason is we are talking about a very, very complicated system. A cybersecurity system that would take in server logs, user details, organizational information, and of course, resource details, logs, files of various different kinds. All these systems, the traditional ones, are more like two-dimensional in nature. If you want to compare it with something, how they store the data inside to do some analytics on top of it, it's more like a traditional database, right? It's more like a RDBMS, or maybe a smarter tool like a business intelligence tool where they're keeping all this information in RAM and coming back to you with some kind of analytics on the top. But that's no more the case. Tiger Graph plays well with your existing cybersecurity system as a complement or a supplement, in which this data, this information can be stored inside Tiger Graph to do deep link multi-hop analytics, which I'm going to demonstrate to you very soon. And that would generate enough signals for you, enough rules for you, enough machine learning based feature extraction for you to detect anomalies. Let me show you why a graph database can actually do it rather than any other existing technology. So let's take a basic analogy of what RDBMS is and what a graph database is. So at a very top level, on the left hand side, you're seeing some graph, RDBMS. And the biggest challenge with RDBMS is that you cannot fire ad hoc queries on them. It has to be normalized in a certain way before you can get away with the joining problem, the ledger kind of row, the rows and columns of RDBMS tables. Find me an IP address who has accessed a particular application more than 500 times, have spent a session which is longer than 30 minutes, and run at a weird time of a day. Fire a query like this on RDBMS table and see what's going to happen, right? It's going to be extremely complicated. You will make millions of rows into billions by making the joins and put a filter criteria on top of it to get to the information you need. Virtually impossible. It just doesn't work in the economy of scales. Secondly, your NoSQL data stores are basically not going to have that kind of interrelatedness inside the data set. Graph, on the other hand, is created it's a natural storage model for connectional data. If your data interlinks and interconnected, graph is the way you want to go because this is data-centric model. Each IP address and all their services are connected by just one hop away. And one hop away from those services are the resources that they have utilized. So imagine this as an in-memory location, identifier-based location, from hopping from one point to another, one entity to another, rather than joining the data sets together in an RDBMS join. So that makes it thousands of times faster than a typical RDBMS database or NoSQL database, which can be used to do this kind of heavy analytics. So that's where the graph databases shine over these technologies. What is the motivation? I'll just sum it up very quickly in 4 or 5 simple steps. Data set is huge. Again, your total cost of ownership has to be bearable. This is a costing exercise, right? This is operational cost. This is not necessarily, or compliance and regulation, not necessarily generating a revenue. So you need to run it on a system which can handle this kind of huge data sets and still perform at scale and speed. So if you are looking for such a system, then graph database like Tiger Graph is your only choice. Integrating multiple data sources. By nature, graph connects the data. Now, it's natural storage model for connectional data. So when you bring in data from different sources, you do not have to do special massaging. They can very easily interlink and interconnect together. And again, interconnection on multi-level data structure. Hierarchies are respected in a graph. Graph by nature is hierarchical. So that is another advantage of using the native parallel graph. And last and not least, is you're required to do deep link analytics. You need to expose the hidden pattern inside your data set. Find me these two IP addresses I have. Tell me automatically, without firing a query, how are these two connected? Right? When that is something, a shortest path distance when you store data in graph structure. So this exposing of a hidden patterns inside your data set is the biggest advantage which graph databases provide you over the traditional set of defenders that you have, the analytics on top of the defenders that you can generate. Common attack pattern, all of them are doable in graph databases. I'm going to demonstrate a few of them to you today. So I have a demonstration for you where I have created a graph database, which kind of mimics this scenario. I will explain the detail as we go into the demo. And we will be doing a match user behavioral pattern, how a certain user is interacting with your system. Trace the source of error or alert inside your system. It's a very complicated exercise. Anomaly detection will do, how it's varying from the standard deviations. And also, as Gaurav was mentioning in the beginning, the graph feature extraction, which can be fed downstream into your machine learning algorithms to generate even more smarter threat detection exercises. So let's get into the demonstration first. Sorry about that. All right, so here is our Graph Studio. I hope you can see my screen right now. And what you're looking at is called a Graph Studio. I mean, this is one of the part of Tiger Graph. I mean, it's one of the most important part of Tiger Graph where you're going to see, where you can create your schema. Schema is necessarily a use case you're going to develop, map your data, because data has to be coming from outside. And of course, you need to load data from external sources. You can explore the graph, build patterns, and write the queries. There are many different capabilities in this solution. I will suggest not to make up a mind of whether a feature exists or not exists. Just reach out to us later and we will show you how it can be customized for your own needs. So I'm going to explain this use case from an event-centric view. Their event is, it's just in the middle of this map. You know, this view is, you can just call it an alert-centric view or IP-centric view. It's as good as that. It just even happens to be in the middle. And these events are generated by various different services. Event can be generated from a service. Service can generate an alert. You can see all these attributes on top of them. And alerts can be related to a server. And of course, event can be from a server, to be from a server, and alerts have a type, and event uses resources. It has information about resource utilization. There are devices, IP addresses, and user related to this event. So it's a very simple use case where the data can be coming from various different homogeneous, heterogeneous data sets. But the idea is whether it's about your application log, whether it's about your server log, all of them are generating events. And there are alerts of various different types who are getting merged together and stored in our system over here. Next stage is mapping the data. We have a very smart and open source connector frameworks. You can bring data from any different format into Tiger Graph. But right now here, I'm showing you a CSV file from where the data is getting mapped into our system. And here is a service ID going into the services. There is the name of the services, firewall of the service. There are ETL tools available over here to make this exercise and do this mapping together. There are filtering criteria and various different factors into the system. Now let's go. There is a smaller data set which I have loaded into the system, a few thousand entries. And I just wanted to show the exploration. How does this actually work? So what I'm going to do is I'm going to start with the user IDs. And we are going to pick up one particular user. Let's pick up the user number 11. As you can see, this is an entity. This user has generated various different events. And this event is associated with the device number 16, an IP address, and of course, there is a resource utilization. And there are server details. There are more information regarding services. So this is how the lay of the land for this particular user and its one particular request looks like. Now, if you go to this IP address, you may be able to see how many more requests this IP has generated, what this device has been up to. See, this device has generated various different alerts in the system. And all these events, oh, sorry, these are not alerts, these are events. And all these events have their own detail related to IP address. So the idea here is not to show you a pretty user interface, right? As I was explaining earlier in the beginning, what you are seeing over here, the data actually stored in this format, the visibility, the visualization is just a byproduct of the schema what you created. The power and the value of the system lies in exposing the hidden pattern inside your data set, that too at a scale. So what does that mean is that I'm going to my system and saying, show me the hidden pattern between event 46 and a IP address 100.164.82.69. Let's say I don't know if this path exists or not. All I'm saying the system is show me the path between them up to a level 6 hop. System goes ahead and expose the hidden pattern over your record set in matter of milliseconds. We don't go into table joining. We don't go into linking the various different data sets. The way data is stored is interlinked together. So now it's much more easier for you to find exposing these hidden patterns of the data set. Now, this is just a byproduct of storing the data in graph format. The real value of graph lies in the deep link analytics, as we started with that Solargate example. Now, let's look at a particular use case where I have an event. Let's say the event is, let's talk about data is corrupted. Some data got corrupted. Now I want to find out which IP address is related to this data corruption. So since the data is corrupted, there are many people who may have accessed it. So there are events generated who were reading this data and then writing to this data. So if you look at the flow, what we're going to follow is from alert, we will get to the resources which are related to this alert. Then we will see who did the right event, what are the users associated with it, when did they log in? They have to log in within a week. And what are the IP addresses they're associated with. So going that many hops down in your data set based on a programming logic, which is very much parameterizable. This is a G-SQL programming language in which this logic is written. It's very much like SQL. I'm putting a 7 days limit, and I want to find the top 3 IP addresses which are associated with this data set. Here goes the output. I ran it under sub-second. System comes back, showed the interlink and interconnectivity between the data set. And if I put it in a tree view, you will find out what happened behind the scene. This is the data corruption event. This is the data corruption event that occurred from these services. From these services, we went to the resources it utilized. From the resource utilization, we were able to find out which is a login and a non-login event. And once that event takes place, we are able to find the user associated with it and go to the IP address it is related to. So very easily, we're able to find out all these details, interlink and interconnected together. In interest of time, I'll be walking through very quickly from some other use cases. For example, flooding detection. We want to find out addresses which flooded one of the services in large request. Over all the data set, I already executed the query, and here is the output. Now here is the IP address who has 41 times flooded a service, one particular service, whose mean is 3.7, actually 4, and standard deviation is 10. So you can see how much this guy is away to find out how the flooding, to conclude that this IP address is flooding the particular service. You can do it on all your services. You can do it on 1 or 2 services, but the idea here is to show at the speed and scale at which this system performs. Not only visually, these are JSON output. It can be integrated very well with your system. Let me see footprinting detection. This query detects ID that calls for many endpoint of services in short period of time. Like who is hitting my services a lot between this time frame? Here we go. Again, the output in JSON format. User number 1 hitting service number 13 14 times, though the mean is 4 and standard deviation is 11. So you see the speed and scale, how we go down your data set, join them together, conclude, and come up with the result. You can use this very well with your machine learning algorithm or just an analytics or a rule. Each of these flooding detection, footprinting detection can be a rule or a query inside Tiger Graph system. Very quickly, let's get back to why Tiger Graph, why not other technologies where we are better, because we are a C++ based engine underneath, so we are extremely fast and efficient. We are a distributed graph. That means that you can technically expand us endlessly. So you get the benefit of graph distributed processing, MPP architecture, and we provide you in-memory machine learning. And that's where Gaurav, as was initially mentioning, OLTP, OLAP, and machine learning algorithm joined together. With that, what I'm going to do is going to tell you how to get started. Please go to tgcloud.io, and over there you will see the cybersecurity toolkit which I just presented to you. You can spin off one of your servers. Once you log into the system, there is a free options available over there. You spin off the TG Cloud cybersecurity toolkit, and you will be able to run what I was showing you today. With that, thank you for joining us today. And I will give it back to you. Petrika.
Awesome. Thank you so much, Abhishek and Gaurav. We really appreciate you sharing your insights with us and sharing this awesome product. All right, for the audience, it's time for you to head to your next session. So go ahead and make your way there. Along the way, feel free to connect with our awesome sponsors, check your connection requests, and do some virtual networking. Thanks so much, and we'll see you around.